Hello, hope you're all doing well today. This lesson is on the basics of reading graphs. We went over this in class a little bit today, but just as kind of review and to lock it down in case you have any questions on that. Some of the graphs we're going to be looking at eventually in this unit are the displacement or position graph that we looked at today. Then we're going to be looking at the velocity time graph and finally the acceleration time graph. We're not going to get into all of those in this lesson, but those are the graphs that you'll have to be becoming familiar with. So let's create a graph here. Here we're constructing the horizontal axis. We're going to call that time in seconds. All these graphs that we're going to be building for motion, kinematics, the study of motion, we'll have the time graph on the horizontal axis, just like this one. Now in this one, the vertical axis we're going to call position. That's position in meters. And you're going to see that I'm going to mark 1 through 8 meters here. So we're going to be moving somewhere between 0 and 8 meters and going from 0 to 10 seconds. Now time always moves forward. Time can't move frontwards or backwards. Position can. We can go one direction and then another. Time will keep moving forwards, however. So we will take a look now down in the bottom left-hand corner. There's Mr. Jones, and he's going to be taking a little trip here. So you can see Mr. Jones at a starting place, got a little arrow to mark a starting place. Time hasn't begun moving yet. We haven't started measuring it yet. So we'll just say he's at the origin right here on the graph. I'll put a little dot right there. He's at his starting place. Time hasn't begun to move yet. If we consider each one of the lines in the graph down there below the wavy line to equal 1/2 meter, we can see here that Mr. Jones has gone 1 meter. So let's say that took him 1 second. So after 1 second, he will have gone 1 meter. So we'll plot that point right here, 1 second and 1 meter. So he's gone 1 second. He's covered 1 meter of ground. And now after 2 seconds, you can see that he's covered another meter. Remember, each of the squares is a 1/2 meter. So he's gone 2 meters in 2 seconds. So we'll plot that point where the 2 meters and 2 seconds place intersects. And after 1 more second, you can see he's covered 1 more meter, gone 2 lines, each a 1/2 meter. So after 3 seconds, he's covered 3 meters. Now let's connect those dots in the graph, and you can see we basically have a straight line. As you realized in class, we'll call that a linear equation. A straight line represents the fact that the speed is not changing at all. Mr. Jones' speed, once going from 0 seconds to 3 seconds, has remained constant. Therefore, we have a straight line. Now let's suppose Mr. Jones wants to stop here for a little while at this spot right here, about 3 meters down the road, and he wants to rest for a while. So time keeps going. So even though he's not moving, time's going to keep going. So after 4 seconds, we'll have a plot there, but he hasn't moved, so the position doesn't change. After 5 seconds, he would be in the next spot, and again, time hasn't moved, so he'll still be in the same place there. Get my pen to work here. And then after 6 seconds, he'll be in the next spot here. There we go. And so after 3 more seconds, he hasn't moved at all. So if we connect those lines, you can see that for seconds 4, 5, and 6, he stayed in one place, so that all of a sudden the graph is now flat. The slope has changed to being flat, showing that he's not moving at all. The position hasn't changed. Time has to keep going, though. Now let's suppose Mr. Jones decided he wanted to go back where he came from. Now you notice he's moved back from the place he stopped, but he's only gone back a 1/2 meter. So let's say in the next second he only traveled 1/2 meter. And so if that's the case, in 1 second he would have only gone about a 1/2 meter, so he would have gone to that spot about a 1/2 meter farther away. Now let's say in 1 more second he went another 1/2 meter. So now he's after 8 seconds he's returned a full meter although it took him 2 seconds on the return trip to cover a full meter, where on the first part of the trip, as he's going away, he covered a meter every second. Now you'll notice that the slope of that line, although it's negative, isn't as steep as the positive slope when he was moving, because he's not going as fast. He is going in the negative direction now because he's going back to where he began, but he's going at a slower pace. Let's see what happens if he continues at this slower pace. Okay, now you see that after 2 more seconds at this slower pace of going a half meter every second, he's gotten back to within 1 meter of where he started, even though he traveled longer than at the beginning. So in 4 seconds, he's only gone back 2 meters. So, and you can see that the slope of that line is, this line right here is not as steep as the slope of this line right here. Now, if you remember that the slope is rise over run, or the y-axis divided by the x-axis, you can see that for this, the slope would be meters divided by seconds. Well, that happens to be our units for speed or velocity. And so if we take and divide, for instance, in this first section that we see right here, that he covered 3 meters in 3 seconds. So if we take 3 meters divided by 3 seconds, we will see that Mr. Jones is traveling 1 meter per second. Now, in the second part of the graph, this part right here, he covered no ground, so that would be 0 meters in 3 seconds. That would equal 0 meters per second. Now in the last part, in 4 seconds, he covered 2 meters, but he was going in the negative direction, so we'll say that's a negative 2 meters. So he went a negative 2 meters. He took 4 seconds to do that. 2 divided by 4 equals 0.5, but it's going to be a negative 0.5 meters per second. So you can see the slope in the first part of the line was a slope of 1. The slope in the second part of the line was a slope of 0, and the slope in the third part of the line was a slope of negative 0.5. But now we can see from our position time graph that we've determined the speed by figuring out the slope. So if we have a positive slope in a graph, you know that you're going to have a positive velocity or speed. If you have a 0 slope, it's going to be 0. If you have a negative slope, it's going to have a negative velocity or speed going back in the negative direction. So if we consider the basic outline of our graph here, we're not going to worry about numbers right now. If we take a steep slope in a linear graph, we know that he's got constant speed, but we know he's going pretty fast because of the steep slope. If we take a shallow slope, we know that he's going slow because it's taking a lot longer to cover the same amount of ground. So by looking at the slope, you can tell, is he going fast, is he going slow? The greater the slope, the faster he's going. If the slope happens to be negative, let's say, let me use an orange color here. Let's say when time begins, the object is moving and then it starts slowing down, we would end up with a negative slope. So the orange line shows an object that starts at the 0 time moving, but it's going slower and slower and slower. That's how we get a negative slope on the position time graph, till you see he gets down to the end, he's not moving at all when he hits the, well, he is moving, but he's still moving in that negative direction. So the slope of the line can tell us how fast in what direction he's moving, or if he's not moving at all. Remember, if it's a flat line, if it's a zero slope, he's not moving at all. And then if we divide the position by the time, the distance by the time, we can actually figure out how fast he's going. So those are some of the basics of the position time graph. I hope it made it clear. Go do the review now. I've got a couple of review problems for you to do, and then take the little quiz at the top, and you'll be ready to go. Don't forget to hit the submit button.